winsock, specifically the darker sides of winsock, namely the service provider interface. I strongly encourage all of you guys that have their laptops here, and that's pretty much most of you, to go to that URL right here, where you have the lecture notes in PDF. So you have essentially the slides plus additional notes, which is most of them I'll be talking about, but it also has a source code sample and so forth. So anyways, what I'm going to be talking about right now is mostly Windows oriented. Now, how many of you guys are actually Windows programmers, perchance? Okay, the rest no. How many of the winsock programmers have actually used sockets before? Okay, fairly okay. So for all of you that haven't used sockets before, I mean, much as I'd like to start tabula rasa and start, fresh with everybody, I can't do that because of the highly technical nature of the talk. What I can do is just give you a bunch of introductory terms and the nomenclature we'll be using here. So most of you that already know this are just going to have to, just bear with me for 3 or so slides. But the way it works is that all IP-based communications, all internet-based communications on your PC are essentially made up or are implemented by using what's known as a socket model. The socket model is an API that was originally developed for Berkeley sockets, as in Unix platforms, and it's very similar in all respects to a file handle. So essentially when people want to transfer data, transmit data over a network, be it UDP, TCP, whatever, they open a socket. That socket later on connects to some remote host, and they do the data transfer. And the way that works is that the application can just read and write to the socket just as it would to any other file descriptor, with the whole underlying mechanism being transparently implemented by the OS. So if there's any need for fragmentation, encapsulation in either VPNs or IPsec or just plain IP and whatever transport you're using, the whole thing is done transparently. Now, the way the socket model works is that there is a Berkeley socket model, which is a standard socket API, and that's been implemented in many RFCs and a bunch of, some of you may know Stephen's books, Unix Network Programming, and of course TCP/IP Illustrated, which is like the tome of sockets ever. And essentially the same model that used to work for Unix also works in Windows, only Windows adapted it into something that's known as winsock, namely Windows sockets. The way that works is that Microsoft pretty much took the very same API, and for winsock version 1 they actually took the open source and just implemented it as their own. In fact, to this day, a lot of the command line FTP utilities, namely ping, FTP, and all that, are simply ports of the Unix sockets. So winsock 1X was a very close adaptation of the BSD API. That's gone now. With winsock 2 started sometime on Windows 95 OSR2 or Windows 98, but the point is that it is the current standard. And it is a standard that has deviated a long way from the standard BSD sockets due to the fact that it had a lot of other additional new features. Some of those new features, which we're not going to be talking about, are the asynchronous calls and callbacks that any Windows programmer obviously has to implement, as well as overlapped I/O, which is a very nifty feature. But what we are going to be talking about is something very specific called the layered service provider. The layered service provider is going to be our focus here, the focus of this talk. And it turns out that this is a very modular architecture. In fact, it's very nice. I mean, it's probably one of the greater achievements in Windows, at least in my belief. And it provides a powerful hooking functionality that is unlike any other. You could think, those of you who are Windows programmers could think about it as a set Windows hook, only for the socket calls themselves, namely for all the socket API, from socket creation through the data reception, data receiving, connection, asynchronous I/O, whatever. Everything is implemented in a way that you can pretty much hook it very simply. Now, unfortunately, the LSP, while it was thought of and contrived with a lot of legitimate application uses, turns out that most of the people that do use it to date are mostly the illegitimate people, namely those who try and distribute spyware and spying and all that jazz. So the focus of this talk is essentially to present the LSP. We start off by presenting it very technically from a feature set, what it can do, what it should do, following by a discussion of the API, a few code samples, and later on I'll tell you what it also can do that I'm thinking Microsoft did not have in mind, at least initially. So, By the way, I should note that if you've got any questions whatsoever, you're just welcome to raise your hand at any time and just interrupt me. So the way that works is that, some of you may know this, the way that works in Windows is that we have the stack approach, in which we have the underlying hardware, which is essentially your network card or whatever, followed by something called NDIS, which is a network driver interface specification, and the TDI. The bottom two that you see there, NDIS and TDI, are essentially kernel-based components. We won't be getting into those, but they have a lot of functionality. They are essentially the socket implementers. So if you work at the NDIS layer, you'd probably be better off, implementing kernel stuff such as firewalls, etc. In fact, most of the checkpoint VPN and all that go into the NDIS and the TDI. However, the NDIS and TDI, as I've mentioned, are both kernel-based components as opposed to the actual winsock, which is user mode. User mode essentially means that it runs in the context of a process, not too privileged or anything of the like. Now, we have winsock on the right here, and we have something called NetBT, which is NetBIOS over TCP/IP, on the left. NetBT is something that Windows uses internally to implement the two basic components of the workstation and the server service that you see right there. Which actually I should use the mouse for this. So WKS and SRV are essentially the workstation and server service, which Windows uses, of course, for all its RPC and its file sharing and all sorts of other buffer overflow written applications. However, on the right here, we have all the basic applications. These could be your IRC, your Mozilla, your Opera, other contemporary browsers, FTP, email, whatever, which essentially all use the very same winsock DLL. It's known by many names, we'll get into that in a sec, but essentially it's either winsock.dll or wsock2_32DLL, and through a very rich API, which is this layer right here. Where's the mouse? Hello, mouse. Oh, there it is. PowerPoint's just acting weird. So you have the very rich API here, and that API is essentially whenever an application wants to do anything, it would call that API, starting with WSA startup, following by whatever socket calls, and so forth. Now, if we go deeper into that, we see that the whole winsock, the DLL here that we see, is essentially something a lot more complicated. And an in-depth look into that winsock DLL can show us that while it has an API, which is the thing right here, it also has an SPI, which is a service provider interface. That is to say that this winsock DLL of ours, the WSOC232, is essentially only a multiplexer by which you have the API calls that are redirected onto various service providers. These service providers are in turn also bound onto the transport SPI and namespace SPI that you see down there, and only after that do we actually get to the TDI and NDIS and so forth. Now what this means for us is that essentially all throughout these layers we can inject our very own code. Specifically we'll be discussing the transport SPI right here. And by injecting our code, we can intercept communication at the socket level. Now, the primary advantage of doing it at socket level and not, say, at NDIS, actually there are several advantages. Other than the fact that you would not want to get into the kernel, you also have the ability to see things from a socket-oriented perspective. That is, you don't have to deal with such stuff as IP fragmentation and packet sequencing. You just get it as a stream, if you're using like TCP sockets, or a bunch of independent datagrams, which is really good. Now the way that works is that we have the transport, which provides for the actual communication. That is all the send, send to, receive, receive from calls. And we have the namespace, which works with all the get XXX by YYY, namely get host by name, get socket by name, etc., etc. And so the way that works is that we have these two, and the SPIs are essentially multiplexers in themselves to one or more providers, and I'll demonstrate that very shortly in an example. Now, going further, we can see that a dump bin on WinSock232DLL, I actually might want to do that full screen so you'll be able to see. So if we try and dump bin, which is essentially try and see all the exports that we have, let me just change directory here. So if we dump in and look at the exports that winsock has. So what I'm doing right now is I'm going to that DLL, which is Windows System 32.
WSOC to DLL. Hold on, that would be WS2, sorry. Okay, and I will just rep the specific provider API. We'll see that the same winsock API that exports us a lot of things also exports us a bunch of provider APIs. Okay, now these are mostly undocumented. It's not really, it's not really accurate to say they're undocumented so much as the fact that most people don't pay attention to that documentation. And as you guys can see, we have several there. We have install provider, and we have deinstall provider, and we also have write provider order. Now we'll be talking about those in a second. Now the way that works is that essentially we can install additional providers. We can install our very own custom DLLs that would work as transport providers and that would implement or at least filter through all types of data transfer. And by doing so, of course, we can have pretty much control over the entire network API. Okay, so the way that works is that, as you can see on the slide, we have a bunch of them, and actually did here a grep -i install, and you can see that we have the install namespace and the install provider, as well as the deinstall provider and uninstall namespace. For some reason, Microsoft isn't really consistent with their own API. So these are all exported, and of course we'll get into these in a second in the sense of what function prototypes to expect and so forth. And there's a very handy utility in the platform SDK, which is part of the part of Visual Studio that you can download, called SP-Order. SP-Order is both the name of an executable, which I'll demonstrate in a sec, that you see here, and also a very handy DLL. SP-Order standing for Service Provider Order. So what we do here is essentially we can enumerate those providers, and using the DLL we can also rewrite their order. Okay, so the effect of that would be that we can essentially install our own hooks or our own DLL with hooks as a custom provider anywhere in that chain. Okay, and let me just demonstrate that by calling that little executable here. And so going through that, we'll see that I'm just calling this purorder.exe. You can see a bunch of providers here. I hope the font comes out pretty well because there's no maximize here or anything. You can see the core providers, which are the TCP for UDP/IP, TCP/IP, and RAW, which naturally some of you will recognize as the SOC stream, SOC datagram, and SOC RAW. We have RSVP, which is essentially a Windows 2000 attempt to enforce quality of service. Not too useful, but still. And we have a bunch of others here which I'm going to ask you to ignore because they're due to the fact that I have VMware. So VMware has its own custom pseudo interfaces, and these are the GUIDs, the global unique identifiers that are just appended. So these we're going to ignore, but the ones that we're interested are essentially the TCP and the UDP/IP ones. Naturally, also the raw socket ones is really useful if you want to implement ICMP and so forth. And so the way that works is you can see that these providers are essentially DLLs. Specifically here you have MSW-SOC DLL, which is the actual DLL that does all the jobs. So winsock itself is just, remember, it's just a top-level shell that works sort of like as a multiplexer here. And we have a bunch of service flags and so forth, which I'll not get into. I have a demo that documents it pretty well, and I'll discuss that in a second. But also know that we have the address family here, hex2 meaning AFINET. We have the protocol, which is of course 6, and for UDP we'd have hex 11, which some of you will recognize as, of course, the UDP protocol number, and so forth. We have it as either a stream protocol or a dgram protocol, and so forth. So all this is fairly nice, and this is where it gets complex, because from here on we can actually do stuff that may have been intended and may not have been so intended at first. So we start off with this SP-Order DLL. This SP-Order DLL is essentially a DLL that came from the platform SDK, but is now pretty much ubiquitous with all sorts of spyware. Some of you may know that DLL because it comes bundled with CASA, not the CASA Lite version, which is spyware-free, but rather the one that is spyware-ridden. And so the way that works is that this SP-Order DLL is really important due to the fact that it exports just 2 functions here, which are the ones that we want. And just a sec, where's my pen? And so the way these 2 functions are, oh wait, it's black on black, so much for that. Oh well, whatever. It was worth a shot. Anyway, so there's a way to change the color, but never mind that. So you'll just have to look here. So there's write namespace order and write provider order. That enables us to essentially not only installer providers, but also have full control as to their respective location inside this little chain. Now, if we also look at the imports, okay, you'll notice that these are the exports, namely what the DLL exports to other uses. However, the DLL itself uses a bunch of other imports, specifically some from kernel 32 and from ADV API, which is of course the registry DLL. So the way that works is that all this provider mumbo jumbo is actually implemented in the registry somewhere, and that I'll discuss in a second. Okay? Any questions thus far? Okay. So, going back to our little drawing there of what the winsock API actually looks like, we see that we have the transport and the namespace SPIs, and we have the base providers, but we also see that for transport providers, we can further enhance existing providers by applying something known as a layer, and essentially implementing a layered service provider. And this is essentially the potency and also the weakness of winsock. Because by implementing one of these LSPs, I can essentially filter through the data. I don't have to implement anything. I don't have to implement the actual data transfer. I can just pass it through once I'm done with the data, but I can get the actual data just before it goes to the application, or just after it comes out of the application and gets sent to the network, which is really, really strong for us. Now, of course, the original intent of that was to be used in like quality of service, encryption, security, custom protocols, and so forth. But the actual implementation is that we can essentially install those service providers and the application remains totally agnostic. Okay, the application remains totally unaware of that. And that is essentially why it's being used in spyware, due to the fact that most spyware would want to collect your surfing habits and so forth, and this is exactly what it can do. Applications go on behaving normally and using the winsock API normally, not knowing they're affected by this, which is, of course, what the spyware people just want. So, how do we do that? So, we have this rich API that winsock exposes us, and that's in the ws2spi.h file. Okay, this is one of the header files you can only get through the platform SDK. So the first call that I'll discuss is enum protocols. Now you'll notice that unlike the WSA, which is the winsock API, this is actually a WSC, okay, which is just for the provider enumeration purposes. And so we have this little prototype here, which is pretty self-explanatory, but I would much rather describe that through a little demo here. And so I actually have the demo right here, and for those of you with the notes pages, it's just a sec. So those of you with the note pages will note that they have the full source right here. Hold on. It's over like 3 pages long. And so the way that works is, and that for demonstration, I'll just give you the source right here. Let me just put this down for a sec. Okay, so we have this. Can anybody still hear me? Is that fine, or do I need the mic? Okay, I'll need the mic. Well, whatever. So let's just go on to enum LSP here and see that it is essentially a very simple main. It is a very simple main that goes on to enumerate all the protocols, and so each protocol structure is associated with this LPWSA protocol info, okay, which is a long pointer to the structure. So we first off call it with a null just to get the count of bytes requested and so forth, and later on we can actually enum the protocols. And by enumerating the protocols, we have this array of protocols, and for each we just print the protocol info. Now I won't really get into that because this is fairly simple. It just printfs the various fields. But a simple example here will show you that we can. I actually need to make it first. Just a sec. Okay, so what I'm doing right now, I'm just making it. Okay, this is just a quick make. And once I make this, you'll see that I have this exe that essentially gives me the full provider list. And this is essentially the same thing you had from the sborder.exe. Okay, it's a bit more annotated in the sense that it actually expands on the service flags, and you can tell that by the service flags some of these protocols are message-oriented as opposed to others which are not, as opposed to some which support broadcast, those which support urgent or out-of-band data, and so forth. So that's with respect to our little demonstration here. And going further, we would of course want to implement our own LSP, our own layered service provider. So the way that works here is that we have our DLL that we want to implement, and that DLL would, in being a service provider, would have to adhere to a certain API that we would need to implement. Okay, say for example, just like most of you in Windows would implement the win main and so forth, or the message loop, it's the very same thing, only this time you just implement a different API. We start off with the WSP startup, which is the call that corresponds to the WSA startup. And so what happens here is that once the client application would call the WSA startup, that same call would be filtered onto you. Those of you who know WSA startup would of course recognize the version requested, which is the 2.2 or whatever version you need, and would also see that you have the protocol details and so forth. Now, you can do whatever you want here because this is essentially the protocol initialization feature. You can decide that you want to be the sole provider of the protocol. You can just put yourself in pass-through mode, that is, get some of the data but also pass it through to other applications. You can do whatever you want so long as you return no error. If you return anything else than no error, WSA startup in turn will of course also return something else, and the application will fail to initialize winsock. So that's fairly simple, and once you implement the WSP startup, you are also supposed to implement the dispatch table, or what you see there is the upcall table. Now, I'll get to that in a second because I actually have a fully working example of that, but in a nutshell, the idea is that you get in as a parameter the upcall table, and that upcall table is the table of various API calls as implemented by winsock, and you can decide on whether you want to take that upcall table and just maintain it as is, or install your own implemented calls, which are the LP proc table that you see here. So this is a long pointer to a function array, and those functions can, of course, be implemented by you, or of course can be just nulls or path through to the normal applications. And this would essentially enable you to custom fit the API to, say, for example, only intercept send calls, or only implement receive calls, and so forth, if you want. Yeah.
Now, if you're at the stack, do you have any control about what layers under you have after you?
Okay, the question was, if I'm in the stack, do I have any control as to what layers underneath me or above me have? Okay, that was the question, right? So you don't have any control whatsoever on the people above you, but you definitely have control over people below you. Okay, so the way that works is that you can pretty much reorder the stack, the chain rather, as it's called, in any way you see fit, and we'll see that in a second. That's why SP order is so crucial. SP order exports the right provider order, which enables you to put yourself on top of the chain, below the chain, and so forth. One caveat to that is once you're in the chain, if somebody later on installs himself on top of you, you don't know anything. Okay, you become totally unaware of that, and that is actually a fine example of what happens with Google Desktop. Those of you who have Google Desktop, how many of you actually install that? Oh. Okay, well, because we're smart people, okay. But those, let's just say the innocent users who are tempted to install that, so what happens there is that Google has their own LSP, which they use for okay purposes. Their purposes in particular are really nice. It's like when you get into Firefox or Explorer and you do a Google search, it also shows you your desktop as well, as part of the HTML page. Now, the only way to do that would be to intercept the call to Google and actually edit the HTML on the fly. And from what research I did, that this is apparently what they're doing. Now, I should note that I haven't really done the proper research here, but this is like the general idea behind it, and a lot of websites also share my view. Okay, so just to reiterate here, you can control the call stack in the sense that you can pretty much control the chain, but, and the fish, that's, never mind. But the point is that if anybody was to later take control of the stack itself and, like, say for example, decide to implement their own provider on top of me, they would have access to block the calls just like I have access to block subsequent calls and not forward and down the chain. Okay, so what we would do is we'd implement the WSP startup, and of course we'd want to implement that procedure table, essentially to bind our own functions. Those of you who are Linux oriented may note that you have the very same capability in Linux, but from a kernel perspective. Like if you get the Linux IP or TCP handler, you can pretty much get the TCP protocol structure and pretty much hook your own receive and send on top of it. So this is the same thing, only here it's done at the user mode, which is of course a lot simpler for most things. So most winsock 2 API functions will be mapped to your functions by a very simple rule of WSA turning into WSP. That's to say, let's say for example, you want to hook WSA accept or WSA async select, you would pretty much implement WSP async select and of course hook it with the corresponding pointer, which is fairly simple, and I'll show you that in a second. So you can pretty much hijack all the functionality you want, be it the actual socket calls or get peer by name, which is of course really nice to see who's on the other end. Naturally, you can also hijack the accept. So if somebody is actually looking for the peer address and the caller ID, so to speak, you can subvert it any way you want. Setsock opt is really nice to subvert. Address to string is really nice to manipulate, and so forth. Okay? And at any point in time, if you don't want to subvert anything, you can just call the upcall table straight away and just essentially do an extra few commands of just checking your procedure table and filtering through, and the impact performance-wise is barely noticeable, if at all, especially not on like contemporary computers. So, going further, we want to install our own provider, and for that we actually need an additional executable, or an additional sort of like something that would hook our DLL into it. And so the call here would be the WC install provider that I showed you in the export list. Only this is the actual API, and that we'll see in a second. So what we'll do is we'll install our own provider and rewrite or reorder this by calling write provider order, which is, again, to reinstall us in the stack in any location we want. Now, if memory serves, the note page here, okay, actually has an example of how to do that. So what I have here is a small wrapper function, which just takes, as a parameter, it has just an out parameter, which we'll be discussing in a sec, and it just returns an int to success or failure. And what we do here is fairly simple. Our provider would have some random junk GUID, which is a global unique 128-bit identifier, pretty much like everything in Windows, and we would just take our own protocol info, wipe it clean, and populate it with our stuff. So naturally, the first thing we want to do is set the provider flags to PFL hidden, which means we want to be subversive. This is actually a supported flag there for some reason. Additionally, we can do, we put on our own GUID, we put ourselves on as a layered protocol, and we say that in this particular case, we want to hook AFINET, SockStream, IPPro to TCP, which is, of course, the basic TCP socket functionality. We also have a security scheme parameter, which is mostly ignored. I mean, this is security is like, it's a total oxymoron if you ask me. And all we have to do now is just install a provider in the sense of passing this GUID, this global unique identifier, our protocol info, and our DLL name, which unfortunately has to be like in ASCII, in Unicode format for some reason. And of course, we also have the ERR no, which is just to get the error. Now, what we also have from here is we get back a catalog entry ID, and that I'll be describing in a sec when I'll show you the behind the scenes of all that. Okay, and once that's done, essentially, if that little code snippet executes, then that's it. Then your provider is in there. All the DLL has to do is just be accessible, mostly through System32 or any other way in the path. But preferably we want that in System32. Now I should note that what I'm demonstrating here is not some zero-day exploit or anything. It is just plain functionality. You would need administrative privileges for that, which is, well, you know, but everybody runs as admin anyway. Now, probably the first moral that people should take to heart from this is something known as the principle of least privilege, which I'm sure you guys are mostly familiar with. Essentially, it has a lot of applications. The application in our case would be, don't run as local admin. But of course, saying that, I'm willing to bet that 90% of you do run as local admin, but then again, I also do, so, you know, no worries there. Point is, if people do not run as local admin, that will of course not happen, and of course if people don't run as local admin, they wouldn't be half as susceptible to viruses, worms, trojans, or whatever, but it just doesn't work that way. So, going forward, we have our little demo here. Now, instead of writing this nifty open source application or anything, I chose to do something very, very simple, which is essentially take the platform SDK demo and just edit it myself, modify it to my own needs. Due to the fact that it's a platform SDK demo, I will unfortunately not be able to release it because it has like copyrights by Intel, Microsoft, and I'm just still lonely. I don't want to, fuck around with anybody there. So you're just going to have to see the demo, and pretty much all the relevant code snippets are already in the slides. So going into that little LSP directory here, I would like to show you first the DLL main, which naturally, since I'm implementing a DLL, then the DLL main is the most important part of it. The DLL main has a very simple addition. Specifically, it's just the DLL main from any sample project you'd open. And what we do here is we have a file pointer, which we start off as null, of course. And as processes attach to us, that is, as processes would load our DLL, we decide to open a file under the name of sockdebug.something.txt, with the .something being the current process identifier. Okay, so the way that works is any application that would now call winsock using our Trojan DLL, we'd have a C:\\, at the root of the C drive, we'd have a little sock debug file, and of course we'd get all the sends, receive, and so forth. Okay, so all I do here is essentially open the file and do nothing much. Okay, further, we have the core, so further we have the core, which is the spi.cpp. Now you'll note that, again, this is the full platform SDK version. There's nothing really much that I've changed here. But what I did do is that I took WSP startup, which is, of course, our first function here. WSP startup is right here. And, okay, this is like the very same comments that Microsoft put there themselves. And notice that we have here we save the upcall table, which is the table that is given to us by winsock, and we put our own table here. Okay, we make sure we're in the provider catalog, and just a sec, there it is. And so you see that we have the LP proc table, which is, again, is an in parameter for us, an in-out parameter rather, and we just decide to link its LP WSPA accept into our WSPA accept as well. Okay, and just we can do that simply by putting all the functions one by one. They don't have to have the same name. This is, of course, just for pure legible reasons here. But essentially, you can implement whatever you want, and each of those functions in turn will be called when the corresponding API function will be called. So this is really nifty. So just as an example, let's go further to examine how we intercept WSP socket or WSP send. So looking through WSP socket, for example, which is, oh, wait a sec. We want to do it up here. Okay, so going back. Okay, so, okay, yeah, so this would be it. This is WSP socket. So what I do here is essentially not much, so much as just write some, oh, there it is. WSA socket call interceptor. That's all I did here. The interesting stuff, of course, would be WSP connect and WSP send and receive. So looking through WSP connect, which we probably need to, you'll have to excuse me for using Notepad. It's like the only reliable application I could find. So WSP connect is right here, and what we see here is that we have this little addition here, and so we get the WSA connect on the socket, and we of course get the internet address. Okay, so what I do here is that I have the name parameter passed to me. I overlay struct sockaddr in, which is of course what I need to for IPv4 addresses, and I can intercept that connection and tell exactly from which port it came and so forth. And last but not least, we have WSP send or WSP receive, which are essentially an identical implementation, in which what we do is we have buffers. Okay, we have these three parameters. We have the long pointer to the buffer array. We have the buffer count, which is essentially the number of entries in said array. And we have the number of bytes sent by the application. And so what I do here is fairly simply just to debug print all of what I found in the buffers. Okay, fairly simple. Okay, I printed character by character due to the fact that it may be binary data. And so if I would print with a %s, I'm likely to, buffer overflow or something. I don't want that. So essentially, this is like a very simple example. Now, going into that, then, we have our little LSP DLL right here, which is right there. And of course, we can also make it, and that doesn't really matter. And we have our installer application. Our installer application would be right here, inst.lsp.cpp. Now, this is a very simple installer application, which again, I have not modified in the slightest from the actual demo by what's her name, by Microsoft. And as you can see here, essentially they have the very same protocol info and so forth, and a call to WC install provider. That is it. Okay, nothing more. And I also have an install new chain, which would further reorder me. So what I do here, and that we should just go a bit further down, is following the WC install provider, okay, following the installation of my provider here, we have the provider reordering, okay? So as you'll be able to see here in a second, after the registry bullshit here, which is really not interesting, we enumerate the existing protocols, which is of course using WC enum protocols. We get the protocol chain, and for each, we install our own new chain. Install new chain will in turn call install provider, and of course set us up there. Following that, okay, we just make sure that everything's enumerated correctly, and we just do the reordering here, which is right in this little thing. WC write provider order. Now when we do that, we ask for, we actually supply two parameters, which are the catalog ID buffer, which is an array of catalogs, and also the number, which is of course the size of said array. And that'll be described to you in a second how that works. So in order to facilitate the demo, let's just do an install here. And while I do an install, I would also like to use REcon, which is the sysinternals tool, which is really useful for all things that have to do with the registry. So I have it set up to go with the inst.lsp.exe. And as I install this, you'll see that my little application here is essentially enumerating those providers and installing over each. Now again, this is like a very mock application, so it's by no means any efficient or anything like that. And you notice that it also does the global unique identifiers. That is all sorts of VMware interfaces, which I wouldn't normally be interested in, although it is nice to know that I can hook them. I should also note that VPN types, say for example, client VPNs that open a virtual adapter for you, are very much susceptible to it, because in this case, you would hook them before they actually get the chance to apply encryption. Okay, so this is a major caveat. Now looking through the little REcon dump here, we see that mostly all this was going for HKLM, HK local machine system, current control set, services, winsock 2 parameters. And so here we have the protocol catalog and the namespace catalog. Going into regedit, and seeing as it's one of my favorite locations anyway, you can see that we have all these providers enumerated here, and for each provider we have the packed catalog item, which is essentially packed binary data. Rather, in this case, it's a bunch of SZs of string terminated by zeros. So LSP DLL and so forth. Naturally, we can do that with the SP order DLL. Most spyware applications take that DLL, but it's fairly easy to implement that DLL on your own, in which case a lot of anti-spyware applications would not, have any idea that you're actually doing that type of sinister thing. So now that we have ourselves installed, and you'll notice that we have ourselves installed over everything, we reordered the chains and of course saved the new protocol order. If we just go for a second to enumerate, as I have before, with the exe naturally, not the source, then we'll see that we have our layered providers. Now you'll notice our layered providers now come first. So before we get to the actual TCP/IP, which is the MSAFD TCP/IP, we go through our layered provider right here, which is of course providing us with full control over the stack. Yeah, you have a question there? Oh, define our place in the order of things? Yeah, we're first. Essentially, what that means. Yeah. Again, no. What I'm. You could check. I'm not saying you could check. That exactly. The whole point of this presentation is to make people aware that they should check that. Do they check that? Probably no. Okay. Chances are 99% don't check that. In fact, some of the anti-spyware solutions I've tested don't check that, which is of course ludicrous. I mean, so what are you protecting against, right? Now, as you'll see here, it's fairly easy to enumerate and find that. Okay, if you do explicitly enumerate the stack, yes, you are aware that a provider is there. However, the question is, do you do that? And the answer is probably most applications don't. Yeah, that's right. Well, the hidden flag at some point would just work with other forms of enumeration that you'd be invisible to. But let's not get into that because let's take that offline. It's like in depth. Any further questions regarding that before? Okay. Yeah. So we have our provider here, right here, and another thing I did was also to have, as you might have noticed, I'm opening a file in the root of the C drive for each process, and I will also issue a small message box. That message box will tell me the name of the file per application. So all I need to do right now is essentially launch my favorite browser. Oh, and there you go. I get suddenly this sock debug 1336.txt. This is a message box from my Trojan DLL, okay, which would actually go under the process ownership of Firefox right now. So I open that, and Firefox, of course, launches, and there you go. You have the Mozilla start page, which is, of course, the default. Now, unbeknownst to the user, we have a little sock debug. We should have a little sock debug, and there it is, 1336.txt. Now, if we'll go into that, I'll notepad it. It's really hard to type with one hand here. Okay, I'll notepad it, and you'll see that it has those captures, okay, including all sorts of types of captures you weren't really expecting. Say, for example, local loopbacks that Firefox has been using for its own RPC and stuff. So we have that. And then, of course, we have this little call, which is the call to www.mozilla.org. And there you see the get start HTTP, the whole thing, cookies, schmookies, whatever, they're all in here. Now, the data right here is a GIF data, okay? The GIF 89A that you might be able to read right here if I move the notepad is GIF data. So, of course, this little application of mine also gets that in binary form. But the point is that whatever I would do from now on in my Mozilla, say, for example, I would go to some, I don't know, some random site, whoops, like so. So as I do that, you can see that my little text file here grows in size. Now, of course, I can do that with Mozilla. I can also do that with, I don't know, with, say, Messenger or Yahoo Messenger or any other. Now, you'll notice this is really funny because this actually goes under the Yahoo Messenger theme. Okay, it has the very same, style because of the message box coming out of the window class that Yahoo registered. Okay, so this time you'll see it's 3844. And another socket that was there, and here's my contact list, which, mind you, is now publicly accessible because I can pretty much see that through here. I think it was 3844. Okay, so this is the YMSG. This is my Yahoo ID. All the other bits were taken. They really were. No, I didn't get your message. Now is not a good time. Sorry about that. Okay, so yeah, let's disregard that for a second, okay? Although it would be interesting to see, that this little sock debug actually got my little correspondence with this person, which we'll be able to demonstrate. That really was not planned, honest to God, it wasn't. Okay, so you can see, Yahoo trying to go for all sorts of Yahoo radio and all sorts of really, really weird stuff. This is like some HTML page that Yahoo takes. And if we go further down, no. Get a hint, woman, get a hint, okay? So you can see right here that did you get my message and now is not a good time and all that, okay? So it's all there. Now I was going to demonstrate that with Messenger as well, I mean with, just MSN Messenger, but now I shudder to think about the consequences. So you're going to have to excuse me there. So all things considered, okay, this is like a very simple application that I did. Mind you that it's all out there. I mean, the platform SDK sample is there. All I did was simply put on my own Trojan DLL. And it would also work with various other applications, although I should note that some encrypted types, such as Skype and so forth, are less vulnerable to that. Any questions thus far? Okay. So, to conclude, because I really don't want to keep you guys, okay, so this of course was a demo, and you have most of it in the notes pages themselves, so you can pretty much apply it. If any of you actually want to apply that for any other purposes, you're welcome to drop me a line. My email, especially for this lecture, is like on the last slide. We'll get to that in a sec. So, just to conclude, the security issue here, I do believe is quite clear to all. No matter how you code your application, no matter what you do, okay, so long as you know you're just a plain winsock programmer, it can be Mozilla, it can be any IM application, this essentially makes you vulnerable to full socket hijacking, which I do believe is bad news. It doesn't really matter if you're on a client socket or on a server socket. An attacker can intercept your calls, can redirect your connections, can filter your data, can do a lot of other really, really nifty stuff with you. Now, the possible, what I call the lawful good uses of this in D&D terms would be, of course, to implement a user mode application firewall, which, you know, rather than work at the TDI or NDIS layer, you'd want to be socket aware, which is, of course, a major advantage. Some applications actually do that, but of course, if you want to be, you know, performance-wise, you're better off doing that in the TDI or NDIS anyway. So apparently, that's not too good a use. Then, of course, there's the transparently add encryption to applications. Now, bear in mind, this was developed by Microsoft around 1998, before the advent of IPsec. So now that we have IPsec, I do believe this use is pretty much, you know, extraneous. We don't need that. You can enforce QoS, and then again, you cannot. And you can, of course, support other types of protocols. I strongly recommend you guys read RFC 1606 or RFC 1149 if you haven't yet. They're both hilarious. But theoretically speaking, yes, you can support IPv9 if it comes out. I should also note, mind you, that this stuff, the socket hijacking and all that, also works with IPv6. My machine has had IPv6 installed up till recently, and the same thing works for IPv6 sockets just perfectly. So unless Microsoft changes that with winsock 3, we're likely to still be vulnerable. Last but not least, we can also patch content on the fly, and as I've mentioned, Google Desktop does that. However, bear in mind, this is a double-edged sword, because Google can add their own, you know, search to your desktop, whatever, but an attacker can also do a lot of other interesting things, namely, can rewrite entire web pages, insert rogue cookies, do cross-site scripting, you know, whatever you want, it's just plain there. So the chaotic evil uses would be, of course, to patch content on the fly, for obvious uses. But also, you can obtain connection statistics, URLs, and so forth. This is what most spyware people do. Fortunately, spyware people are only semi-illegitimate, in the sense that they only want your statistical purposes and want to know where you've been, but which, of course, they could do a lot worse. They could steal a lot of other data. Well, then again, they might, so you never know. Of course, you can eavesdrop on any connections which are non-SSL, and including some of the connections, as I mentioned, which are VPN-based over adapters. Okay, so bear in mind if you have one of them, I don't recall what mine is here, but I do have this type of adapter connection here, right here. I don't recall what that is, but that's TAP Win32 adapter, whatever. So that is essentially a VPN connection. When I enable that, it really connects and it does all the encapsulation, but you know, it's useless from this perspective. And finally, and I believe that's the best application of all this, it would be to reroute connections. Reroute connections, namely, you have the user typing in mozilla.com or .org or whatever, but in actuality, it's rerouted to some other place. And of course, if the browser would go with get peer-adder, the browser would find that it's still connected to mozilla.org, whereas it's actually connected to microsoft.evilempire.something.com, you know? And so, just to conclude, the dark side has never been so tempting before. I mean, all things considered, a lot of people are pretty much unaware of that stuff, and I thought that it would be kind of like an interesting tidbit that some of you might like to know. Other than that, if you have any questions, comments, flames, whatever, SPI at SecurityNet is, the SecurityNet is where you can download, of course, a PDF with the notes pages, and the SPI mailbox is just explicitly for comments on that, and flames and spam, potentially. Questions? Yeah?
If you wanted to do things after the kernel lookup, where like if you wanted to set your IP IDs to all 0 to prevent, you know, NAT fingerprinting, this would not be the correct?
This would not be the correct. Okay, the question was if I wanted to do stuff post-kernel processing, namely if I want to set my IP ID to 12 zeros or whatever, that probably would be best implemented at the NDIS layer. However, bear in mind that at the NDIS layer, I would only have access to per packet basis, which would mean that I would have to impose the struct IP header myself, and I would have to decapsulate and so forth. I would have to deal with fragmentation. I don't want that. Okay? Any other questions by other guys aside from my partner here, whom I really don't know, but he's asking nice questions. So, questions?